Great. Thanks so much for the really, really nice introduction. And also thanks for the invitation to speak here. It's really great to be here, at least virtually. So yeah, as you just heard, I'm going to be talking about these new CMB lensing measurements that we made with ACT, and I'll discuss what they mean for structure growth and the S8 tension. So the papers that I will be discussing are these three, discussing the measurement and its implications for structure growth, the lensing map and the broader combined parameters, and the mitigation of the key systematics foregrounds. And I should emphasize that this work was done by not just the broader ACT team, but really by a large team of sort of CMB lensing experts. So first of all, I really should acknowledge my group members, Dongwon Han, Neil McCran, and in particular, my student Frank Q, who really did a lot of the heavy lifting and led a lot of the key analyses, as well as my great collaborator, Matt Manavacharo. So here's an overview of what I'll be discussing today in this talk. After a quick introduction to the S8 tension and CMB lensing, I'll discuss the challenges to our measurement of lensing, and then and how we overcame them. And then finally, I'll discuss our results and what they mean for cosmology and structure growth. All right, and with that, let me just start us off with a bit of an introduction to this area. So I'm sure everyone on this call knows that the vast majority of the mass in our universe is invisible dark matter. And I'm sure you also know that it's really interesting if we can use gravitational lensing to map out this distribution of mass, because this mass distribution contains clean information on some of the key open questions in cosmology. For example, what are the properties of dark energy? What are the masses of neutrinos? Is GR the correct theory of gravity? And what are the properties of dark matter? So we'd really like to make these gravitational lensing measurements of the mass distribution. And often this is done with galaxy lensing, although I'll talk about CMB lensing today. Now, one thing you can do if you measure one of these lensing mass maps is you can constrain parameters. For example, you can constrain the neutrino mass or the dark energy equation of state or something like that. But you can also do a more general agnostic test for new physics, a general agnostic test of whether your cosmology predicts structure growth correctly. And this is a particularly powerful test. So let me describe this really, really powerful test with a really long redshift lever arm. It works as follows. So in a first step, you fit a lambda CDM model to CMB power spectrum data coming from redshift 1100. So you fit a lambda CDM model to high redshift CMB information, and then you predict how structure should grow in our universe all the way down to low redshifts. And then that sort of gives you a predicted indirect value of sigma 8, which is the key parameter we'll be talking about. It tells you sort of the clumpiness of the mass distribution, the RMS fluctuation on 8 megaparsec scales. So you have this predicted sigma 8 from a high redshift extrapolation, assuming lambda CDM, and then you can compare this prediction with a direct measurement of sigma 8 from direct lensing measurements at low redshifts. And this is a really interesting consistency test in general to see if you agree or not. The prediction and the direct measurements agree or not. But in recent years, it's become even more interesting because there are hints that something might be going wrong in this comparison of sort of predicted high redshift extrapolation versus direct low redshift measurement. And so what's shown here is a summary of basically the determinations of sigma 8, or more precisely S8, which is sigma 8 times omega matter to the power of 0.25, which is what lensing really determines best. So you can see the different measurements from different experiments shown here on the right. And they're color-coded in different ways because they're physically very different measurements. And in green, what you see is what I call predicted sigma 8, which is an extrapolation based on a fit to high redshift data, assuming a standard cosmological model. So this is sort of the prediction. And then in blue, you can see the direct low redshift measurements from galaxy surveys, including from several weak lensing experiments. Now, the intriguing thing, if you look at this plot, is that many of these results are coming in low. compared to the predicted values in green. So, it is worth emphasizing that each of these measurements on their own is just 2 or 3 sigma low, and they're not all independent. But it's notable that, there really is a trend. There seems to be a bit of a trend, and people have found, I find this quite intriguing. So the question is, what is going on here? Is there something wrong with large-scale structure growth? And is the explanation for this just fluctuations? Or is it a sign that there are systematics in one or both or many of these measurements? Or is this a first sign of new physics, a first sign of the breakdown of lambda CDM? That would be the most interesting possibility. And so in this talk, I'll try to ask the question, can CMB lensing help clarify the situation here? And how can this work? All right, so now let me switch gears a little bit and give you an introduction to CMB lensing. So CMB is really a unique source for the study of gravitational lensing for 2 reasons. First of all, it's the highest redshift source that we can observe. And so it lies behind all the mass, basically, in the observable universe. So that's one unique aspect compared to galaxy lensing. But it's also unique because we really understand it, I would say, particularly well. We know exactly what redshift the CMB comes from. And we understand the linear physics of the CMB source very well also. Right, so those are really nice aspects. All right, so what happens as the CMB photons travel through the universe to our telescopes? Well, they're gravitationally lensed or deflected by the entire large-scale mass distribution through which these photons pass. And this leads to a net remapping of the observed CMB sky that we see in our telescopes. And I should emphasize, feel free to ask questions and just interrupt me if you have any. All right, so let me show you in a simulation the typical size of this effect. So here's a 10 by 10 degree cutout of the CMB sky in a simulation. And you can see the CMB temperature fluctuations with this color coding here. And in this simulation, the lensing has been switched off, okay? But because it's a simulation, I can turn the lensing on artificially and off. And so I'll switch back and forth now. So here's no lensing. I'll switch the lensing on. So prepare yourself for a dramatic effect. Okay, so that's the difference between with and without lensing. And so what you see, this is a small remapping by just a few arc minutes. So because it's small, I think it's not that useful to look at this to get some intuition for the lensing effect on the CMB. And so to explain this, I like to show a really, really exaggerated cartoon picture of what lensing by a big blob of mass or dark matter does to the CMB. So the cartoon here is that I've put a huge exaggerated blob of mass in front of the same unlensed background CMB, and now I can look at the effect of lensing on the fluctuations. So the fact that lensing deflects the photon's paths means that in the direction of this blob of mass, the CMB fluctuations are characteristically magnified and stretched out, as you can see here. Now, if I want to describe this quantitatively, I can do so with an observable, the lensing deflection field, or equivalently the gradient of a lensing potential. And this gradient of a lensing potential defines a vector field on the sky that describes this remapping. So it sort of points from the direction in which a CMB photon is emitted to the direction in which it's ultimately received. Now, I said this is an observable, but how can I actually measure this lensing deflection field or this lensing potential? So the way this works is the following. Let me first tell you the algorithm that we run, and then I will provide a little bit more intuition for how it works. So the algorithm that we use to measure lensing is what's called a sort of standard quadratic lensing estimator. Basically, what I do is I take a CMB map and I Fourier transform it, and then I look at correlations between different pairs of modes that were not there without lensing. So basically, I just do an integral over a quadratic in the temperature or polarization modes. And this gives me an estimate for this lensing potential. Now, why does this work? So this was actually an explanation provided by, I think, some people on the call. So what this estimator is actually doing in some limit is the following. Basically, it's locally measuring the CMB power spectrum in little patches of the sky. And if a certain direction has been magnified a lot, the estimator knows about this because the local power spectrum will be shifted to larger angular scales than average or shear equivalently. And so this then allows you to go from a map of the CMB to a map of the gravitational lensing. Okay, and so here's an example for one of these CMB lensing maps. In fact, talk about 2011, this is sort of the retro original CMB lensing map that we made back then. And these lensing maps are really the fundamental object that comes out of your pipeline. They tell you basically about the projected mass and dark matter all the way out to high redshifts. So the strength of the lensing encodes information about the projected mass density. Now, of course, if we wanted to do quantitative cosmology, we don't want to just stare at one of these mass maps or these lensing maps, even though they're quite pretty. What we'd like to do is describe them statistically by measuring a power spectrum of this map. So we can do this, and the power spectrum of this map is a key quantity, the CMB lensing power spectrum CL55. So this lensing power spectrum tells you how much lensing you have as a function of the angular extent of the lens. And I'm using multiples, so higher L corresponds to smaller scales. All right, so if I've measured the CMB lensing power spectrum CL55, what does this tell us? Well, because the lensing map tells us about the projected mass, the lensing power spectrum tells us about the projected matter power spectrum. And that allows you to immediately understand the shape of this lensing power spectrum. It's just inherited from the matter power spectrum shape via this projection. Okay, now let me discuss the redshift and scale origin of this lensing signal. So the redshift origin of the signal is shown in this plot here. You can see a breakdown of how this lensing power spectrum gets built up from different redshifts. So what you see really is it comes from a broad range of redshifts. But the mean is quite high redshift. So the mean signal comes from around redshift 2. So CMB lensing comes from pretty high redshifts, but it also comes from large scales. It comes from sort of linear or near linear scales below K of around 0.2. Okay, high redshifts, large scales. And now let me discuss a little bit the parameters that we can probe by measuring the CMB lensing power spectrum. Now, as I indicated earlier, like other lensing measurements, CMB lensing probes the clumpiness of the universe parameterized by sigma 8, the RMS density fluctuation on 8 megaparsec scales. But of course, it's also sensitive to the matter density, omega matter. And so what you get is this characteristic degeneracy curve where you see that you, for a given measurement, can trade off, more clumpiness, more sigma 8 with more matter. That gives you the same amount of lensing. So the combination and the exponent that you get here is a little bit different from the equivalent quantity in galaxy lensing. So because CMB lensing comes from higher redshift and larger scales, we have an exponent here of 0.25 rather than 0.5 for galaxy lensing. Okay, so this means that we can probe sigma, we can probe structure growth very effectively and cleanly with CMB lensing, and that means we can constrain all parameters that are related to structure growth. For example, we can use this to probe neutrino mass, but again, the other thing that we can do, as I discussed earlier, is we can measure sigma 8 and S8 in a general sense and compare these lower redshift lensing measurements with the expectation from a prediction based on high redshift lambda CDM fits. Okay, so this is the picture I showed earlier. And the question is, where does CMB lensing fall on this S8 plot? And how can CMB lensing clarify this intriguing situation that is known as the S8 tension? So what I think CMB lensing can contribute here is that this tension is, generally phrased as a discrepancy between possible discrepancy between Planck and galaxy surveys. But CMB lensing is very much independent, right? Because our ACT measurements don't really depend on Planck. And they're also obviously independent of galaxy surveys. So this is going to be a very much independent data point with very different systematics. And our ACT lensing measurements are also really competitive with the state-of-the-art precision, right? So we'll present measurements that are reaching sort of 2% precision or better on some of these key parameters, sigma 8 and S8 and related quantities. So it'll be an independent and competitively precise probe that will, first of all, help to clarify the possibility of systematics and where they may lie. But even if you set aside systematics and you say, you know, I really think this could be new physics, these CMB lensing measurements will help you clarify, you know, where this new physics could be arising. Because it's worth remembering that all of these different measurements of, you know, how structure grows are really sensitive to different redshifts and different scales, right? And so what CMB lensing is sensitive to, as I said, is it's sensitive to sort of high or intermediate redshifts around redshift 2 and large scales. And so we can directly, immediately test, confirm, or rule out the possibility that there's any new physics that affects structure growth between redshift 2 and redshift 1100 with our results. And you can learn a lot more then by comparing these CMB lensing results with other probes. Okay, so hopefully that's motivated these sorts of CMB lensing measurements and why they're really interesting. And now let me discuss our actual measurements. Are there any questions so far? Okay, so if not, let me continue and discuss our ACT CMB maps and ACT CMB lensing maps and our measurement of lensing. So let me first introduce the Atacama Cosmology Telescope. So ACT was a sort of 6-meter ground-based CMB telescope that sadly operated in the past from 2007 to 2022. So this is a picture of ACT. Here you can see the telescope in the middle. So while the experiment is now gone and we're all switching over to Simon's Observatory, the collaboration that you can see here lives on. And this involves 160 collaborators at 45 institutions, including in South Africa, UKZN. So there's a lot of data that really exciting data that's still to come and that we're working on now. So let me just show a few more pictures and I'll tell you a bit more information about ACT, and in particular about the new release, data release 6, that these lensing papers are really the first part of. So as I said, ACT is 6 meters. It's located high up at more than 5,000 meters altitude in the Atacama Desert in Chile. Here's a picture you can see of the site. You can see ACT is here and SO is being built up over there. This is a great site. Along with the South Pole, it's sort of the best ground-based site. Now, ACT DR6, ACT Data Release 6, which is what we're talking about today, is really going to be a step change for ACT. So we've had great ACT results in the past, but this release I'm really excited about. It's an order of magnitude more statistical power than the previous data release 4. And so, you know, this means that we're deeper than Planck over, you know, almost half the sky. And it really means for parameters that, you know, as you'll see for many parameters, we're either matching or even starting to exceed Planck level precision from a ground-based survey. And this is, I think, a real milestone in the field, because for a long time, Planck has really been the state of the art. So this particular release, even though ACT observes in 5 bands, we are actually only using a subset of the data, a lot more room left for improvements. So we're using 90 and 150 gigahertz data, and we're also only using observations taken during the night because those are easier to analyze. Here's an example for this fantastic ACT CMB data, these fantastic ACT CMB maps that I'm talking about. On the top panel, you can see the temperature map, and on the bottom panel, you can see the polarization map. And so these maps, first of all, as I said, have really low noise. But another thing that's really good for measuring lensing is that they also have really high resolution. And you can sort of just see that by eye because of how many of these red point sources you can just see by eye. That's a sign of how high our resolution is.
Just a quick question. Why polarization looks a little bit higher resolution than temperature?
I think what you're seeing here with these features is actually noise, right? So, yeah, so I believe this is just a property of the noise, and the temperature is just so much brighter that you're actually seeing the signal out to the same band limit.
Okay, I see.
Okay, so we have high resolution and low noise, and that gives us a lot of modes, which means that we have great performance in measuring lensing. All right, so as I said, what we're going to do is we're going to use our sort of curved sky quadratic estimator to go from these nice ACT CMB temperature and polarization maps to a map of the lensing, right? Which tells you about the projected mass and dark matter. So let me now show you our large sky 9,400 square degree CMB lensing mass map, which I'm really happy about. Here you can see this ACT DR6 CMB lensing mass map. Okay, so it covers a quarter of the sky. As you can see here, the color coding, since I'm plotting the lensing convergence, right? So I can, for the experts, I can go from the lensing potential, just like in electrostatics, I can go from potential to density. I can also go from lensing potential to mass density or lensing convergence. So this is really a mass map where these orange colors tell you that you have high density in a certain direction, and the sort of purple color shows you that you have a low density of mass or dark matter in a certain direction. This has been filtered to only pick out the scales that we actually are imaging. All right, so these are real structures of mass and dark matter at high redshifts that you're imaging here. Now, these features that you can see here then correspondingly are also real features, right? This characteristic scale of these blobs is set indeed by the peak of the projected matter power spectrum. So this is at least I'm telling you, a very, very nice high fidelity mass map or dark matter map that we've made with CMB lensing. And I think it's one of the best ones that exists. Well, it's easy for me to tell you that it's really high quality and high fidelity. Let me illustrate this a little bit more and then give you some quantitative information. So what I'm doing here is I'm zooming in on this sort of gray box, this little cutout, and I'm actually showing here the lensing potential technically, but again, this is a CMB lensing mass map or dark matter map. And given that this is really signal dominated and I'm really imaging the mass, I can do neat things. Like what I can do is I can find a galaxy survey that probes similar redshifts, or a galaxy tracer that probes similar redshifts, redshift 2. And we have one of these, which is the emission from dusty galaxies, the cosmic infrared background. And as you know, because galaxies follow the underlying dark matter, what I expect is that the distribution of infrared background emission from these galaxies should follow the underlying dark matter I see in this CMB lensing mass map. And indeed, that is the case. So what I'll do is I'll overplot the infrared background sort of galaxy emission contours on this dark matter map, and you'll see that the correspondence, I think, is really nice, right? So you can see that the contours, which show you a completely different thing, the infrared background emission, really closely follow the CMB lensing, which probes the dark matter. Now, that's not really surprising. I think everyone expects that the luminous galaxies follow the underlying dark matter, but I think it's just beautiful to see this by eye over 9,400 square degrees. All right, let me make this more quantitative when I say that we have a nice lensing map. I think you can do this by just looking at the noise power in our lensing map. So in red, you can see the noise power spectrum of our CMB lensing map on 9,400 square degrees. And you can compare that not just with the signal here in black, but with the sort of Planck 2018 noise level, the last official Planck release shown here in the dotted blue line. And you'll see that this is a factor of 2 improvement. So this is indeed a significant improvement on the noise per mode compared to Planck, although we have a smaller area. And then you can also see what I said earlier, that there's a significant range of scales where the signal is above the noise, so we're really imaging the mass. All right, so this is a really beautiful lensing mass map. And I will talk now about the power spectrum that we get, the lensing power spectrum and the parameters that we get from this mass map. But I want to emphasize, and I'll come back to this, that this mass map overlaps with a bunch of optical surveys, SDSS, the Dark Energy Survey, HSC and KIDS, and that means this unlocks a wealth of really interesting cross-correlation science that I'll talk about later. But for now, let me talk about the power spectrum and the parameters that we can get. Okay, so the DR6 lensing power spectrum measurement. Let me now talk about how we did it and what the challenges were and how we solved them. So on the face of it, measuring a lensing power spectrum doesn't sound that complicated, right? I get my CMB map, I run a quadratic estimator, that gives me phi, the lensing map, and then I just square that and I get a lensing power spectrum, easy. Sadly, it's not quite that easy because basically there's a noise bias to this measurement you need to subtract. A bit more mathematically, the lensing map comes from a quadratic in the temperature. And so if I square that, I get 4 powers of the temperature that go into a CMB lensing power spectrum. And so even if I have no lensing in the CMB, these 4 powers of the temperature have a non-zero expectation value. And so there's a bias, and that's this noise bias. Okay, but that's not a problem. We know how to build these pipelines. We've been doing it for years. We measure lensing, we figure out the noise biases, we subtract them off, we get a lensing power spectrum. That's not hard. What is hard is, given that we've reached, we're reaching sort of few percent level precision, what is hard is ensuring that you really, really trust the measurement that you've made. And so that's where the vast majority of, several years of work went into testing and verifying our results. So in particular, my student, Frank Q, really led a lot of this sort of measurement and the testing of the lensing power spectrum. So we built a blinded analysis framework with an extensive null test suite to make sure that we really trust our result. So what I mean by that is that in terms of our blinding, we were not allowed to compare our results with theory or with other data sets or run parameters until all of these null tests that I'll talk about now were passed. And we're not allowed to, until all of our analysis choices were frozen. So, okay, what null tests do I mean? Well, the nice thing about this DR6 data set is it has so much redundancy in it that you can do a really wide array of checks to make sure that everything is consistent and that you've controlled your systematic. So Frank Chu ran 200 null tests to check the quality of these results. So broadly speaking, you can imagine doing consistency tests like checking that you get the same lensing in temperature and polarization, that you get the same lensing in different frequencies, that you get the same lensing in different regions of the sky, or the same lensing on different scales or in different instrument areas. So that was really the framework that we used to check that our results are reliable. Unfortunately, this did not work at first, and there were significant challenges that we had to overcome that really were particularly stark for ground-based data because of the atmosphere and the high resolution. So, even though lensing from the CMB is generally quite robust, there were 2 major issues that slowed us down for a while. And so let me talk about those 2 challenges, and then I'll discuss the results. So the first challenge is the accuracy of the ground-based noise bias subtraction. The second one is foregrounds. Let me start by discussing the first real challenge that we faced. So the history of this is that, when we started working on this, when Frank started his PhD, we started building this null test suite, and annoyingly, even the very simplest null test we could imagine just failed catastrophically when we started out. And the simplest thing we could imagine doing is, let's just take a map of noise and run it through the lensing power spectrum pipeline. And, we better get 0. But unfortunately, what we got instead were these sort of U-shaped failures shown in green. All right, so this is a map made from noise only, from the data, right? So we take 2 different halves of the data and we difference them, and that gives us a map of the noise. So even the noise was giving us biases, and so everything was a disaster, and we spent a lot of time trying to figure out what was going on. And eventually, even though these pipelines are quite advanced, we realized that the ground-based noise was just so complicated that our noise bias subtraction was not working well enough. And you can see, actually, that maybe this is not surprising that this ground-based large sky noise is really complicated, because the atmospheric noise is really complicated. The scan is not really uniform. at all over the sky, as you can see from the sort of scan pattern that shows you how low and high the noise is as a function of direction. And it's not just the level of noise that varies. It's also the directionality of the noise. So if you look at the sort of noise power in different regions of the sky, it has very different properties. So there's basically no symmetry at all in the properties of the noise, and it's really complicated. And it was just, that was our procedure, even though it could absorb a little bit of mis-simulation, was just breaking down. We were not subtracting the noise bias well enough. How did we solve this problem? Well, we switched to a completely different kind of estimator that is not affected by noise modeling at all. And the way this works is you use only cross correlations between different parts of your data that have independent noise. In particular, in your lensing power spectrum 4-point function, you only use independent noise in all the 4 different fields. And so that makes you immune to noise modeling. And using this, a new estimator, we went from this horrible failing null test to this passing blue one, and now all the null test looked really good. Okay, so noise complexity was the first problem that we solved, and the second really significant problem affecting ground-based CMB at high precision is foregrounds. So what I mean by that is that the CMB photons along their paths are not just gravitationally lensed, but they're scattered by SZ effects in galaxies and clusters. And they're also joined by infrared emission from the cosmic infrared background. And these sort of foregrounds can kind of bias the inferred lensing power spectrum measurement at a significant level given the high precision. And so my postdoc Neil McCran did amazing work at controlling these foregrounds. So let me go into some more detail. So basically, your CMB map is not just CMB, it also has clusters and dusty galaxies that are foreground contributions lying on top of the CMB. So now if I measure a lensing power spectrum, which, as I've said a few times, involves 4 powers of the CMB temperature, I don't just pick up the true lensing signal, but I now also get various foreground bias terms. Okay, now these are not enormous. They're sort of 5% level if I don't do anything beyond the basics, but that's not good enough for us. Luckily, foregrounds really don't look a lot like lens CMB, and there are 2 sort of different approaches that we took to mitigate these foregrounds and to separate real signal from foregrounds. The first method, which is our baseline, is a kind of geometric approach to separating out signal and foregrounds. Basically, you know that, for example, clusters are Poisson distributed, and so you can kind of project out any component that is Poisson distributed from your quadratic lensing estimator. Okay, so you can modify your estimator not to be sensitive to foregrounds. The other approach isn't sort of geometric or spatial. It instead is frequency-based. It uses the fact that foregrounds and signal have very different frequency dependencies to separate and clean out the foregrounds. So we had 2 different approaches that both worked really well. They both, in simulations, gave foreground bias. Here you can see the foreground bias is a fraction of sigma. So both of these approaches, all the approaches that we came up with, gave foreground biases that are less than 0.2 sigma. So that looked really good, but that was a test with simulations. That's one of the prongs of our robustness to foregrounds program. We also have a lot of tests derived from data. So we can compare on data whether we get the same lensing from geometric mitigation and frequency-based mitigation and other mitigation methods. And finally, we can also just target null tests that specifically look for residual foregrounds. And all of these 3 prongs showed no evidence for remaining foreground biases and really convinced us that we are robust to foregrounds, the second challenge. All right, so those are the 2 challenges that we overcame. And now this suite of 200 null tests passed and looked really good, looked basically ready to go. So here's an example where I'm just showing one of these null tests where you can see the difference of your lensing spectrum to the baseline as a function of L for different CMB scales used in your lensing measurement. So you get this consistent lensing spectrum regardless of which scales you use. And that's just one example. So you get consistency across all of these different choices. So here, let me show this more quantitatively. we found a consistent lensing amplitude. So I'm introducing a lens, the amplitude of this lensing spectrum, which is really encapsulates a lot of the information. And so what you can see is that compared to our baseline, we found a consistent lensing at different times. We found the same or consistent lensing in temperature and polarization. We found consistent lensing with different foreground cleaning approaches at different frequencies. We found consistent lensing in different parts of the sky on different scales and so on, right? So all of these 200 tests convinced us that, we are good to go, and that because we're passing the agreed upon null test suite, we are ready to unblind. So are there any questions before I show you the results and what they mean? Okay, if not, let me just go right to the results in a second. So let me set this up first. So we agreed to unblind, and that means we agreed to add data to this theory curve here. So this is, I should emphasize, the lensing power spectrum based on lambda CDM 2018 CMB anisotropies. And this is a predicted spectrum assuming lambda CDM. And so what happened is we all joined a call and we agreed that we were ready to unblind. And then Frank went ahead and plotted for the first time our lensing power spectrum measurements on top of this prediction extrapolated from high redshift. So here are our direct redshift 2 CMB lensing measurements. So I was, really blown away by this plot. And you can see just by eye that you have very, very good agreement with of your measurement in red with your prediction in black. And I should emphasize, again, the black line is a prediction. This is not a fit to the data. It's a prediction. And the red points have no free parameters, right? There's no nuisance parameters or anything you're marginalizing over. You can make this more quantitative and fit an amplitude scaling up this theory curve, and what you get, again, is consistent with 1, right? With the Planck value. This is the signal to noise of our measurement, 43 sigma. So this is very much state of the art. It's comparable to Planck, just a little bit better. It's 42 versus 43 sigma. It's very much a state of the art measurement. In blue, you can also look at subsets of your data. You can look at the lensing spectrum you get from polarization only, for example. And even that gives you a signal to noise of 20, which is far beyond what other experiments can do with just polarization data, at least currently. Again, consistent with the prediction based on the early universe fits to the Planck power spectrum. Let me put our measurement in context. First of all, with the current state of the art from other experiments, you can see our points in red, and the other very precise measurement from Planck in blue, as well as other probes. And broadly, what you see is consistency. I'll go into more detail there, though. Now, in the context of ACT, I'm glad that Inja mentioned this. For me personally, it's been really, really nice to see just how much progress we've made, even just with ACT over the last decade or so. Right? So, when I was a grad student, we were really, really excited about this sort of 4 sigma detection that you can see in yellow, but really this was so marginal, and it's really gratifying to see just how much progress we've made, and that this has really become a probe of precision cosmology, I would argue. All right, now let me turn to the actual parameters, right? So here you can see the best constrained parameter combination, S8 CMB lensing, sigma 8 omega matter to the 0.25, reflecting this degeneracy, this characteristic degeneracy curve in the sigma 8 omega matter space. So this is the S8 CMB lens that we get, 0.818, and the error is sort of 2.7% level. This is sort of as good as any signal, any other single galaxy lensing probe. All right, how does this compare with, so this is a measurement from redshift 2 from the intermediate or late universe. It's a direct measurement. How does this compare with an extrapolation, prediction of structure growth from the early universe from Planck? That prediction is shown here in orange. So again, you see, as you might expect, very, very good agreement between the prediction and what we actually find. And the same is true from a prediction based on ACT DR4. And so here are the values that you can compare to what we find. And again, the message's consistency with primary CMB expectations. So this is a very nice measurement, but can we do even better? Can we get even more precise results? So what we can do is actually we can think about combining our ACT lensing measurements with the Planck CMB lensing measurements. And the reason we can do this is because they have very different information. They have different noise, they cover different sky areas, and they cover different scales. All right, and so assuming they're consistent, which they are, as you can see in this plot, the Planck gray curves and our ACT blue curves with the values shown here, these are very consistent, so we're allowed to combine them. It's not totally trivial how to do this, though. In fact, Frank spent a lot of time figuring out how to do this because you need to compute the covariance. So he did a full simulated mock analysis of ACT and Planck on the same sky, got the covariance, wrote a joint likelihood between these two data sets, and that constraint you can see here in red. And it gives this number here. Again, consistent with the prediction based on the primary CMB, the early time CMB extrapolated down to low redshifts. And this is sort of, to my knowledge, the most precise constraint from a single weak lensing observable, a single weak lensing spectrum that's out there. All right, this is summarizing a little bit this S8 CMB lens parameter that we get here compared to the prediction based on the early universe. Again, as I said, we find good agreement, which first of all seems to indicate there's no systematics at Planck. But I also think it's just worth emphasizing how amazing this is. This is really an incredible success for lambda CDM, just because of so much physics that had to go into this agreement, right? So we're fitting the Planck CMB power spectrum at redshift 1100 with a lambda CDM model. Then we're predicting how structure grows in this lambda CDM model down to low redshift. Then we're predicting the lensing signal this produces in an entirely different experiment, and that agrees to 2%. So I think that's really amazing. Now, if you want to invoke new physics to explain the S8 tension that was seen, what this means is that this really strongly disfavors any new physics explanation that changes structure growth at high redshifts and on large scales. So, if anything messes up structure growth at redshift greater than 1 on linear scales, we would see it, and we don't. All right, let me talk now in more detail about what you get from combinations of our lensing measurements with BAO and with the comparison of our results to galaxy surveys. All right, so our measurement is this red contour. It constrains a combination of sigma 8 and omega matter to the 0.25. If we want to just get sigma 8, we can do so by combining with BAO, which pins down omega matter. So what you do is you combine this red curve with the gray curve. This is a bit counterintuitive, but what you get is this red curve here, because another parameter, the Hubble constant, matters in this degeneracy breaking. So here in red is our ACT CMB lensing plus BAO result. And again, the message is one of very good consistency with the Planck CMB anisotropy prediction coming from high redshift. So we do not find low lensing at all. And the same is true if we combine ACT and Planck with a joint likelihood. And it's remarkable actually what level of sigma 8 constraint we're getting. From this sort of combined ACT plus Planck, we're getting a constraint that's 1.6% level. So this is really, really precise. We can compare in red our ACT plus Planck CMB lensing contour with what you get from an equivalent analysis, but instead of CMB lensing, you use cosmic shear, galaxy lensing. Now, these contours are surprisingly broader. There's an interesting effect where the fact that we have a wider range of scales that we're probing really helps in this combination. And I'm happy to go into more details if you're interested. Here's the comparison. Let me now plot this in terms of S8, the original motivation for some of this work, the S8 tension. So originally, what I showed is just the green points and these blue galaxy weak lensing cosmic shear points. And what you found is that the cosmic shear was a bit lower. But now it's interesting to see that the cosmic shear is not just low compared to primary CMB extrapolation, it's also low at the 1.7 to 2.1 sigma lower, so it's not that significant, but it is that lower at that level compared also to our new CMB lensing results. Let me spend a little bit of time, I've sort of neglected this topic, on other parameters also. So I will just say that we're able to also measure H0 in a very different way. A nice independent measurement of H0 that does not depend on BAO, and instead uses the matter radiation equality scale, which imprints the scale of the CMB lensing peak. We can use that as a standard ruler that depends very differently on new physics to get H0, and that gives us something like 65. So again, coming in consistent with previous CMB-based results. And last but not least, a really interesting thing we can do is we can use our measurement of the amplitude of structure to constrain neutrino mass, because neutrinos suppress the amplitude of structure. So our constraints on the neutrino mass are shown here in green. And you see that this gives you one of the tightest constraints on this unknown neutrino mass compared to other probes. So this, I think, is very interesting, and we're sort of closing in on the minimum mass of 60 millielectron volts. All right, in the last couple of minutes, I want to just give an outlook, what this means with this broad picture for the S8 tensor, right? So the picture that we found is that these sort of high redshifts and linear scales are very much consistent with the early universe prediction, although lower redshifts and smaller scales maybe seem to fall a bit lower. So if there is new physics hiding, it would have, we haven't killed it entirely. It would have to be on smaller scales or at lower redshifts than we're sensitive to. And so I think there's a new outlook now that this motivates not just comparisons of large-scale structure and CMB, but also comparisons of CMB lensing and galaxy lensing, and comparisons of large scales, high redshifts, with small scales and lower redshifts, to gain more insight into whether this could really be a hint of new physics and to pin down where it lies. So something that will be really interesting in the context of this is to pursue cross-correlation science with these new lensing maps. So that's what we'll do next, because cross-correlations allow us to not just probe high redshifts, but they allow CMB lensing to access redshifts below 1 very effectively and probe a new regime. So we're doing a bunch of cross correlations. Now I've already indicated that we have great overlap. Here's an example for a cross correlation of our ACT lensing map with unwise galaxy density maps. And the first thing you note is that you have really high signal to noise. This is a really good measurement, signal to noise of 60 and 64 in 2 different redshift bins, right? Redshift 0.6 now, as well as 1.1. And so what you can do is you can then solve for sigma 8 based on this cross correlation, not at redshift 2 like the other CMB lensing measurement, but now specifically at redshift 0.6. So I can't show you the results here yet, but it'll be really interesting, I think, whether this will come in consistent with the expectation or whether there's some evidence for something weird at low redshifts. So this will be really competitive and really cool. I don't have time to talk about this, but please ask me about another cool thing you can do with cross correlations, which is you can actually probe R. And this is something, the inflationary gravitational wave level. And so I think I'm really excited about this paper that just came out. I don't have time to talk about it. Please ask me if you're interested. And finally, this is not it for ACT lensing. As I said, we only analyzed half of our data. We haven't even analyzed the daytime data. So we can really expect much lower noise and a lot more great lensing science from ACT just in the next year or 2. So with that, I'll leave you with my summary and conclusions. Thank you for your attention.
Okay. Thank you, Blake, for the talk. So again, so maybe we can move to questions. So we have 2 questions. Maybe Gingy could go first and later Brandon.
Okay. Yeah, I mean the last one you have mentioned, Blake, about getting R, which is primordial tensor mode, seems to be very interesting. Can you just elaborate a little bit on what the physics and how the measurement was made? Yeah.
Sure. Yeah. So this, I have to admit, this didn't fit in very nicely with ACT lensing, but I'm really excited about it. So thanks for asking about that. So this is a paper that came out with Toshiya Namikawa recently, the reference I showed earlier. So the basic idea is the following. Imagine that R was 1. So you had a very large level of inflationary gravitational waves. What you could do is you could measure lensing from these primordial B modes, just like you today measure lensing from the temperature. Okay, so right now I can measure lensing from the temperature with a quadratic estimator like this. If R was 1, I could also measure lensing from the deflection of primordial B modes by writing down a sort of BB quadratic estimator instead of a TT1. Now, okay, but we know R is not 1. R is something else. But if R is less than 1, all this does is it scales down the result. So what I'm measuring is not phi, but I'm measuring R times phi. And so what I can use this estimator to calculate an R phi, and I can cross correlate it with G. So I get R times the cross correlation of phi and G, and I know phi cross G, so I can solve for R using this method. Right? And the interesting thing is this works surprisingly well because it's a cross correlation and it depends only on B modes. So you can get R of 10 to the minus 3, and it's basically unaffected by Gaussian foregrounds. We're still investigating non-Gaussian foregrounds. So this seems really interesting. That's
all right. So you just basically correlated the quadratic mode of B, and then with that galaxy, with G's galaxy?
Yes. Yep.
Okay. Interesting.
Okay, thanks. So we can move, maybe move to Brandon's question.
So I would like to refer to this power spectrum plot. It seems that on the left you have larger scales, right? If I'm correct.
Yep. Mm-hmm.
So it seems on larger scales that the data points do more poorly. It seems like the model is underpredicted, or the data is much larger.
You mean these first 3 points, for example, yeah?
Yes.
Well,
is there any reason for that?
Yeah, I guess I would say 2 things. First of all, I'm not 100% convinced that, this is statistically significant. It's always easy to find patterns, and, the chi-squared here would be fine. This is not really a significant deviation. But I think the main thing I would say is the following, and I should have mentioned this earlier. The range that we really trust and that we decided on for our cosmology before unblinding is the one shown here in white without any shading. Yeah. So these gray regions are regions that, just to be conservative in many cases, we excluded because there is the possibility that these could be affected by some level of systematics. So at really low L, like this first data point, I don't really trust all that much, right? I think the possibility here is that, basically this first data point is really affected by the response of the lensing estimator to the mask. And so, basically what you need to do is there's a mask lensing signal that's really big. It's sort of at these very lowest L's. And you know what the mask is, so you can imagine I could subtract it off. But if it gets really large, that's a little bit sketchy. So this point, I wouldn't trust that much. And this is the reason why we focus on the most reliable scales in white.
Okay, thank you.
And I see, just follow up, I see there's a deep band on the left, there's a deep band on the left, and there's a shallow band here, and a little bit deeper band. I believe those are all due to different systematics, right?
So, right. The dark bands we excluded always. But there is this lightly shaded region that, we excluded to be really, really conservative, but actually we have no evidence for our null tests failing in this region. So, as an alternative result, we also do report somewhere in the paper some constraints where we have not just the white region, but also this light gray shaded region. But the baseline result is still the white region. So this is sort of the aggressive range of scales, if you will, the light shaded region.
Okay.
Okay, so any more questions or comments for break? Sorry.
I see maybe
Blake.
Martin Butcher, M.A. Butcher, I think it's probably Martin.
Yes. Well, first of all, Blake, thanks for a really nice talk. And, these results are really exciting. So
Thanks.
congratulations. I guess I have a rather sort of technical question about a detail.
Okay.
So with one of your previous answers, I mean, with the mask, I mean, doesn't one just do, lots of Monte Carlos, and that's sort of included in the error bars? Or what do you think could go wrong?
Yeah, no, that's exactly right. So, basically all you do to get this mean field, as you know, is you just run a bunch of simulations and you Monte Carlo this response to the mask and you subtract it off, right? That's easy. The thing we worried about a little bit is, if I plotted the size of this mean field, right? It's a spectrum that's so red, like it really shoots up here. I think it's like for this first bin, it's like more than an order of magnitude larger. Maybe I think it's 2 here, like 2 orders of magnitude, and it's a factor of a few, and then it's really small here. I think the worry would be, we don't actually know the true power spectrum that accurately. You know what I mean? Like we might know it to 1% or something like that, especially if you include noise. So the worry is not that we don't know the mask. The worry is we don't know the mask times the power spectrum to arbitrary accuracy if this is shooting off to infinity. But potentially this was being very conservative, and you could argue that we do know how to simulate this mean field quite well, and we could have included these points, but we were being cautious.
And can you maybe give a feel for the, points a little farther to the right, how much you subtract off or how much this correct? I mean, how fast does it go down?
Sorry, you're talking about the mean field, yeah?
Yeah.
Right. I don't think I have a plot of this. Let me just see if I have that would be too lucky if I had that. Yeah, unfortunately, I do not have a plot of that, but
if you just a rough estimate, I mean.
Yeah, I think it's sort of percent level or below. It's probably like a few percent for that third bin. And less for higher L's, but I would need to look this up exactly. I mean, it is an extremely red spectrum that just, here it's probably order 1. Generally speaking, I think the cut was chosen where the mean field spectrum is order 1, is the same as the signal. But you can imagine it's sort of shooting up like this, and here it's probably tens of percent, and then 1%, and then negligible.
Oh, okay. Thanks a lot.
I just have a few other quick ones. One is that you mentioned for CMB lensing, sensitivity is on sigma 8 times omega matter power 0.25.
Yeah.
Whereas for lasso structure is a standard definition of S8, which is sigma 8 times omega power 0.5.
Yep.
So what's the major, why there's such a difference? What is that lead to? Is there any physical reason that lead to this different sensitivity?
Yeah, so I mean, first of all, I want to mention that mainly I talked a lot about S8 CMB lens, but if we combine with BAO, we're able to also constrain sigma 8 and the standard S8, right? So we can report all 3 of these observables. But yeah, okay, so where does the different exponent come from? And basically that exponent comes from a combination of the redshift and the scale that you're looking at. So maybe hand wavily, you could say that the lower redshift origin of the galaxy lensing gives you an enhanced sensitivity to the matter density, because you're also affected by, how much dark energy versus matter you have. Whereas if you're looking at CMB lensing, which is basically lives in a matter-dominated universe at high redshifts, the sensitivity is reduced. This is a little bit hand-wavy and not very rigorous, but yeah, I mean, I think there's a general trend of the higher in redshift you go, the less you're affected by changing omega matter. And for example, if you look at Lyman alpha, which is all at high redshift, that isn't at all affected by omega matter. It's only measuring sigma 8. So that would be sort of my hand-wavy explanation. But yeah, it is a combination of the high redshifts and the larger scales that gives us them.
Yeah, and in your table, I see even for the loss of structure measurements of SA, there is outlier of something. The next table, here. Yeah. There is a EBOS BAO plus RSD. This one seems to be a bit outlier of the loss of structure measurement compared to its own peers. Yeah. So any explanation?
Yeah, no, that's a very interesting question. What is going on with this measurement, which is galaxy clustering, right? And it's particularly interesting because very similar data set, the BOSS analysis. So GC is galaxy clustering. And the EFT analysis of this gets something that's quite low. So I think that's a general, it's a somewhat disconcerting fact that different modeling approaches and different RSD modeling efforts seem to result in different values of sigma 8 from similar or the same data sets. It's a bit concerning. I mean, yeah, I don't know enough about this data set to be able to say, oh, this is exactly the driver of why it's different.
Yeah, what's the meaning of GC and CX?
Yeah, good question. So GC is galaxy clustering and CX is cross correlations.
Oh, okay. The galaxy clustering.
I mainly focus on the galaxy, the weak lensing measurements. Yeah. I mean, you could say if you're a big proponent of the EFT efforts, I think, on the theory side, these folks really have it on, do have a great approach. It's very rigorous. So maybe on the modeling side, I think this is really great. On the other hand, this is an official collaboration result, right? So you might say, well, the collaboration, they really understand the systematics and the observational issues of their measurement, and they have access to all these internal mocks. So maybe this is a little cleaner from that perspective. So, I don't know what to trust in terms of the galaxy clustering results. I defer to others for that.
Okay. And really, last one, you say, I see the current likelihood of the neutrino mass seem to be lean towards an unphysical region of below this gray band. So I mean, this maybe it's still not definitive, but this seems to be a sound alarm to me that there may be in the future some problem here.
Yeah, I don't know. I think I have to say that I think a lot of these results are coming from the fact that we're always combining CMB lensing, but also Planck CMB power spectra, right? And one of the weird things in the Planck CMB power spectra is that I think in this case, the high A lens, if you will, the sort of peak smearing tends to push you a little bit to lower values maybe than you would expect. But this is when you're combining with the 2-point function. So it could be that all of these results are driven to want to have a little bit more structure than might be the case, maybe due to a fluctuation, and that is looking like a negative neutrino mass or a very low neutrino mass. So, I don't think it's, probably this is just a fluctuation, and I would assume that as the measurements get better and better, they will, the statistics is going to overwhelm this fluctuation, and it'll sort of converge towards something around here. But I don't know. It's a good question. We don't know what's going to happen. You can say maybe going from green to red, it's starting to go away from, you're starting to peak a little higher. I don't know. A bit of a stretch.
Isn't it completely consistent with fluctuations at this point? I mean, I just don't see something to worry about.
Yeah,
Oh,
I'm
yeah.
not. I'm not. I agree.
Yeah, but what I mean is just from a very adventurous theorist point of view that they're looking for discrepancy. Anyway, so last year Neil Turok was very enthusiastic about this. Neil Turok that he has his new theory of the universe. Anyway,
Yeah,
so
no, I remember that. Neutrinos and the neutrino mass play kind of a big role there, so it's kind of intriguing. Yeah, no, it's a good question whether you could say, oh, maybe neutrinos, we know that they're early on, they decay or something. I don't know. Yeah, like could you explain zero neutrino mass? I think it would be hard.